And now I'd like to point out some observations about the diagonal matrices in relation to the multiplication of diagonal matrices. So remember, for the diagonal matrices, I introduced the following notation, which shortens things a lot. So where I specify only the diagonal entries of a matrix and I ignore those zeros. For those of you who don't remember that, the conventional writing for this D matrix, which is given by this shorter notation or shorter writing, will be this conventional writing. It's a matrix which has zeros everywhere except the diagonal, and on the diagonal you have these little a values. So it's a square matrix like this. Yeah. Now, here's my observations in relation to the diagonal matrices. I'd like you to keep in mind when you do eigenvalues and eigenvectors is this. If you multiply a matrix, so if you look at something like this, and I'll just take you what I'm talking about here, this symbol, it's a matrix in which the rows are given names. It's the same writing as on the previous slide. So if I multiply any matrix with n rows, and doesn't matter how many columns in this matrix, by a diagonal matrix from the left-hand side, if something like this happens, then this is the same as if you multiply each individual row of that matrix by the diagonal entry of the matrix D. So you see, when you multiply a matrix, this symbol stands for, this writing stands for a matrix. So each of these capital R's are rows. So they are matrices of size. This little bit, let's just ignore this. They are matrices of size 1 row m columns. If you multiply a matrix by a diagonal from the left-hand side, this is the same as if you multiply every row by the diagonal entries. You see, this is a matrix of size n times n. This is a matrix of size n times n times m. Similar thing happens when you multiply a matrix by a diagonal from the right-hand side. When you take this factor and put on this side. But the effect this time will be on columns rather than rows. So look at this. If I have a matrix given in column structure, so column 1, column 2, column n, again this is a matrix of size m times n. If you multiply this by a diagonal one, this is the same as if you multiply every column by the corresponding diagonal entry a1, a2, an. Here it is. So if you want to see the summary here, the summary is this. If you multiply a matrix by a diagonal from the left-hand side, this is the same as multiplying each row in that matrix by diagonal entries. If you multiply a matrix by a diagonal from the right-hand side, the same effect, but on columns. You multiply each column by the corresponding coefficients. So see here, they are column vectors. They are column vectors like this, and this last bit is irrelevant. They are vectors like this. Now, one of the consequences of this observation is this. If you multiply two diagonal matrices of compatible size, if you have a diagonal matrix with entries a1, an, and another diagonal matrix with the entries b1, bn, one of the consequences of this observation is that the result of multiplication of two diagonal matrices will be another diagonal matrix where the entries on the diagonal will simply be entry-wise products of a1, b1, a2, b2, an, bn. In particular, another consequence now of this fact is that if you're looking for inverse of a diagonal matrix, from this line, you can see that the inverse will be another diagonal matrix where you individually invert every entry. Of course, this will only work when the diagonal entries of your original matrix are non-zero. And you can easily verify that, of course. The other interesting thing is, which I will type up because I don't have it on my slide. If you compute the power over diagonal matrix, it again comes from here, comes from this line. It will be diagonal matrix again, where the individual entries are just taken to the same power. So A1 power k, A2 power k, how many? N power k. That's how you compute the powers of a diagonal matrices. So this slide actually summarizes the total arithmetic about the diagonal matrices, which is very easy. Everything is done effectively in terms of the individual entries of a diagonal matrix.